Okay. Good morning, everyone. Do you hear me well, even in the back? Okay, fine. Yeah. So, welcome to GeoPython 2023. My name is Kamya, and I'm one of the lecturers of this course. We will be lecturing this course together with David, who will be exceptionally with us today remotely via Zoom. That's why you're seeing this screen right now. But in the rest of the lectures, we will be all here. So I will give the stage to David. He does all the introduction. Yeah.
Okay, yeah, thanks, Kamyar, and welcome everyone to the GeoPython 2023 on my behalf as well. Sorry that I'm not able to be there in Helsinki this morning, but I'm joining you from my rather small hotel room in Italy, and I'll be back in Helsinki next week. So yeah, I mean, today, as you might imagine, our main goal is to kind of introduce some of the things we'll talk about in the course, give some background material and things like that, give some introductions of the people that are involved in the course. And then at the end of today's lesson, we will do a little bit of hands-on stuff, get your first taste of Python. So hopefully you've already had a look here at the slide about what we're going to cover, and we can go into that. I'll ask if there are any questions. Perhaps, Kamyar, you can feel free to interrupt me and make sure that questions are asked, because of course I can't see anything in the classroom, unfortunately, today, but I'll be very much looking forward to seeing you all next week. So as Kamyar has mentioned, my name is Dave Whip. I'm the instructor for the GeoPython part of the course. So for the geology students, we register in this GeoPython course, and then Kamyar is handling the Automating GIS Processes 1 course, and they both run at the same time in the same classroom during this period number 1. So whether you're in one course or the other, you're both in the right place for today. I don't know that we need to say too much more maybe about us, but there are also 4 course assistants. And I think for those of you who are students in the course, you will be interacting with them with some regularity. So I, again, don't know who all is there, but maybe for the course assistants, do you maybe just want to, I don't know, make yourself known and say who, what your name is and which course you're associated with?
Yeah, they're all here. So
Okay, so yeah, maybe Mikko can start.
Hi, I'm Mikko, a second year master student in geography, and I'll be course assistant on both parts of the course. And I was also a course assistant last year. So feel free to ask me almost anything.
okay.
Hi, my name is Levi. I'm actually from Geophysics instead of Geography, finishing all just my master's studies, and well, you can ask me anything as well, not maybe about this stuff, but everything else.
Hi, my name is Veeti, and I'm a first year master student. I took the course last year myself in both parts, and yeah, we would do probably mainly the Thursdays exercise sessions in this period, and maybe the next course as well.
Yes, and I'm Aina. I'm a first year. So feel free to ask me.
Yes. Yeah, thank you. Yeah, you can continue, Dave.
Okay, great. Yes, thanks very much. I can mostly hear what was going on, so that's good, but thanks. Yeah, so those are the people that are involved, of course. Again, for the students, you'll be interacting with the course assistants with some regularity, and we'll talk about that in just a second. But I did want to indicate a couple things as well here about our course websites. There are a few courses that are related to one another. So the first thing that we're in right now during period 1 is this GeoPython course that also runs as Automating GIS Processes 1 in the geography program. and its webpage is here. We'll take a look at the course webpage in just a few minutes. For those who would continue in the GIS part, for the second part of the Automating GIS Processes course, there's a separate webpage for that, autogis.github.io. And for those of you who are interested in the master's level quantitative geology course, GeoPython is also the kind of forms the basis for that course, and it has also its own webpage here. And yeah, both of those, AutoGIS 2 and the Intro to Quantitative Geology course, run this year in period number 2, so starting in very end of October. A few other practical things here. So of course, hopefully you found your way to the classroom. Mondays at 9:15 is when we will have class, which works out, I think, quite nicely this year, because in years past it's been on Wednesdays, and it's been a little bit then tight for students to have time to look at the exercises before the optional work sessions, which are on Thursdays and Fridays. So we'll have our lessons on Mondays where we introduce the material for the week, and also we'll introduce you to the exercise for that week. We'll have one exercise for each week of the course. And then on Thursdays and Fridays, we have these optional work sessions. So basically you can drop in to either one. Doesn't matter if you're registered to one or the other. You can come to both of them if you really want extra help that week. But they run from 12:15 to 4 on Thursdays and from 10:15 to 2 on Fridays. And those are basically just sessions where the course assistants are present, and you can work on the exercise for that week, ask them questions, and just get some help. It's often just helpful as a student to be there, that other students are working on the exercise. So maybe it's just good that you kind of take the time to do it during those work sessions, or at least get started on the exercise during the work sessions, because normally they'll be assigned on a Monday and they're due the following week on Monday. So if you get it done in the work session, of course, that means you don't have to work on it over the weekend. Yeah, then just a little bit about the two courses. Kamyar, I don't know, do you want to say anything about what you cover in the second period course? I mean, we'll go through a little bit of what we're going to do in period 1, but do you want to say anything just in general about what period 2 covers?
Yeah, so the two courses will be similar. Of course, the second course will be continuing on what you are learning in the first period. In the first period, you will get familiar with Python and the basics that you will need in the second course. In the second course, you will be mostly focusing on performing GIS and geospatial analysis using different Python packages. So it will be a bit more advanced than the first period course. Yep.
And yeah, again, to combine, then that makes 10 credit points if you take the two courses together. For those of you who might be interested in the quantitative geology course in period 2, again, it's master's level course. And there we do two things. We do a little bit of geostatistics, and then we spend the rest of the course, after doing the geostatistics stuff in the beginning, looking at ways we can take things like equations, like here, the diffusion equation, put that into Python, and then use it to explore geochronological data and also geological processes. So this is just an example of diffusion applied to how alluvial rivers channel slopes evolve over time, for those of you who that means anything to. So it's basically how we can explore how equations work using Python. Again, it's also 5 credit points. And if you have more questions about the course, you're welcome to ask me, or you can also take a look at the course webpage. And same goes for automating GIS processes. But now this takes us to our first opportunity to get a little bit more information about you. We have this real-time poll, and I will make the question there live now. So if you go to this webpage, either with your phone or web browser or whatever you prefer, we'll ask you to fill in your responses to our first question, where we're just trying to get a little bit of information about who all is present and which course they're enrolled in. So yeah, maybe a bit over half the group that's there now responded, and it looks like majority right now would be students from the Automating GIS Processes 1 course, and some students, of course, from the bachelor's program GeoPython course for the geology students. So yeah, this is probably maybe not quite representative. I do think there are more students enrolled in the bachelor's program course than listed here at the moment, but you get some sense of who all is enrolled, and probably there should also be some students from Aalto. I don't know whether maybe they've registered with these course codes and they're not putting themselves into the Aalto edition of the course, but yeah, I mean, this gives you some idea of who is who's who. Maybe now I'll switch us to the next question. And that's about how much programming experience you have. So for those of you who are in the room now, you can let us know, yeah, how much experience do you have with programming? So yeah, this is a nice thing to see overall, because I think this is very much representative of what we normally get in the course. So there are some people who have no programming experience at all. That's great. The course doesn't assume you have any programming experience previously. So there's no need to panic or anything if you haven't written any lines of code in the past, because we basically try to introduce the basic programming concepts and how to write programs in Python during the course. And for those of you who have a little bit of experience, maybe some of these things will be familiar, some of the kind of basic concepts, maybe things that you have kind of come back to you as you're going through things in the course and remember how it worked from what you've done in the past. But what we hope is that no matter what the case is, that all of you kind of learn and you gain something. For those who are already experienced, who have quite a lot of programming experience, there's likely still going to be things that you pick up and learn. And we try also to include some optional exercises so that those of you looking for a bit more challenge can find it that way. But this is, again, very much representative of what things look like typically in the course. All right, so let's do another one. Now, about which programming languages you've used before. So for those of you who do have experience with programming, what have you used? So again, this looks quite a bit like what is typical for us. There's Python and R as the kind of leaders. They're very much the popular languages to be using for people in geosciences and in geographical sciences. I think it's all, well, they're basically just widespread in terms of the use. Depending on what direction you go, R might be more popular than Python or vice versa, but they're clearly prevalent. Java and JavaScript, I guess, would be often the case that people who have taken some of the computer science courses at the University of Helsinki, I know for a while they were teaching things in Java, so it's possible you've had exposure to that there. But it's good to see that there are some people who have also had some maybe C or C++ or C#, MATLAB or some other programming language. And of course, yeah, some of you with no experience would have none. Yeah, nobody in the Fortran group. I think maybe I'm becoming a dinosaur with having some Fortran programming experience. Okay, I think I've got one more question for you, and that is here about your expectations for this part of the course. So for period 1, what are you expecting and what would you like to learn? And this is just a free-form response, so you can type in what you like. And if I'm not mistaken, if someone types in something that you agree with, you can also tap on it to vote for one of the options. So yeah, what kind of things are you hoping that you'll learn in the GeoPython course? Okay, so we still have responses being posted, but we can already maybe see a few things emerging. The basics of programming as a sort of top thing that makes good sense here, because that is one of the core things we try to teach in the GeoPython course. Integrating Python to GIS is something where we'll get started with maybe the foundations of how to do that in the first period, but really that's going to be something more that's going to be handled in the second period course, where the focus really becomes more about GIS applications. But the first part is really to kind of build the Python background to be able to do that next step. So, some of these other points here about, automating GIS using Python, I think that's perhaps more the focus in period 2 than it is in period 1. But in order to make sure that you have the background to do that, that's the kind of key part about period 1. And yeah, I mean, things like handling large geospatial data sets will be certainly something that you get into more in the second period. Processing big data, we kind of, again, build the foundation for how to do some of this stuff, but it's we also try to make sure that it's accessible and that everybody gets the same background before we jump too far. And although nobody voted on it, building reproducible code blocks is something that we are likely to do. I mean, we're going to introduce things like how to create your own functions, which are in essence a way in which you can just take a piece of code where you have to do a certain thing over and over again and make it into a function. So it's very easy to reuse and apply in many different ways. So yeah, that's great. I think now we maybe know a little bit about you, and thank you for your contributions to the voting. And I'm just going to take a quick look here. I think maybe this would be a good time before we go into some slides about the goals of the course and things like that, to take a look at the course webpage. So I hope that this is big enough. I think the screen in there looked like it was pretty good size when we were in the classroom last week. So hopefully you can see this okay. But this is the GeoPython course webpage for 2023. And if you have loaded it, yesterday or something like that, if you happen to have gone here, you may want to refresh, because lesson 1 should now be visible and you should hopefully be able to see that. But this is the place where all of the course information will be consolidated. So we don't have Moodle. We don't have any of these other kind of platforms that we're using to post our course material. Everything is on the GeoPython course page. So if you have a question, that should be the first place you go and have a look, because you'll find everything from general information about the course and learning goals to specifics about each lesson and exercise, all organized here on the course page. And if we look at the general information, for instance, you'll see here the same things that were just in the slides. So when and where we have our class sessions, including the classrooms where the work sessions are going to be held, who all the teachers are, and the course assistants, and then the course websites that we use in the first period. So that stuff is all here. And I suppose that's going to be helpful to look through at some point. We also have our learning goals here. So this kind of goes week by week, explaining what it is that you would learn that week. So if you're curious to see what we're going to cover in the course, we try to make it so you can only see the lesson for the current week when we reach that week in the course. So like lesson 2 and so on, these are hidden right now so that we only see lesson 1. But if you want to know what we're going to cover, you can look through the learning goals here and see the things that you would be able to do by the end of the course. So that might also be something helpful. In terms of the grading for the course, it's using the normal 6-level grading scale, so from 0 to 5. And the grade between 0 and 5 will be based on 60% from our weekly exercises. So each week in the course, we have an exercise, and then there's a final course exercise or project that's worth 40% of the grade. And that's assigned in the last week of the course, and usually it's due a week or 2 after that. So that'll form the basis of your grade, in case you're curious about that as well. One thing that is new to the course page and new to the course this year is the use of AI tools, or these kind of AI-based large language model tools. So these are things like ChatGPT or Google Bard, maybe tools you've used yourself or at least heard of. but we have added a statement about the use of AI tools in the course this year because ChatGPT has really become much more widespread in its use, and the university has even published some guidelines for the use of these AI tools. If you're curious, you can, for instance, find this article linked in Flamma about how artificial intelligence is being applied and influencing teaching and studying at the university, which includes links to the guidelines for the use of AI tools from the University of Helsinki. So for us, our guidelines are listed here on the course page just to make it perfectly clear to you in the course. And I just wanted to sort of highlight a couple things here. We'll come back to this later when we look at the exercises and things like that. But just to note that the use of things like ChatGPT, these AI large language models, they're not meant to be used in the course for the exercises or to answer questions in the course exercises unless it's clearly stated. So essentially, a lot of the things you could do in the course, you could do using these large language models. And we would prefer, and in fact, we basically are stating here that you should not use those tools unless it's indicated in the exercise that you can use an AI tool or large language model to do a specific question in the exercise. So this is mainly here because we want to make sure that you actually learn the basic concepts of how to write code in Python so that you can understand what the code that would be produced by one of these kind of tools does. So although you could use the ChatGPT or whatever to produce answers to the exercises, most probably you're not going to learn very much doing it that way. So we will indicate in some cases with this AI LLM OK, which is obviously quite a long abbreviation, but this is the indication that you can use something like ChatGPT or Google Bard for one of the exercise problems or part of a problem in one of the exercises. So you really have to look. It'll be indicated in bold and clearly in the exercise when you can use those tools. And we would like to give you some opportunities to use the tools during the course, but we just have to be careful about how and when they're used so that we make sure that you're actually learning what you should learn from the course. As stated by the university, when you use these tools, even if it's listed as okay, you should still indicate in writing which tool you've used and how you have used it. So we will leave space in the exercise for you to enter that information to remind you just to put it in. And as a reminder as well, if you use the tools like ChatGPT, Google Bard, or whatever, in a part of the exercise where it's not allowed to be used, or you fail to report that you used it, this is essentially equivalent to cheating, and it will be unfortunately handled in such a way. So again, we will try to be very clear in the exercise in the places where you can use these kind of large language model type tools. And if you want more information, there's a couple links here to the guidelines for the use of AI in teaching from the University of Helsinki, as well as some instructions for students. I did want to highlight here, though, that with the large language models, we also will try to provide some kind of introduction, for instance, for how to use ChatGPT to produce Python code. So we'll demonstrate this in one of the lessons during the first week where it's possible to use ChatGPT in the course. So we'll show you basically how to interact with it, how to produce code and things like that. And also the way in which you should report what you've done and how you've used it. So we're still thinking about this. Like there's a note here that says, this is basically all new stuff for this year in the course. So we're going to try to find a way to make sure that we embrace the possibilities, but don't compromise the learning outcomes for the course. And so that means, things may evolve a little bit during the course in terms of the guidelines may even be updated during the course. We'll do our best to communicate that if that does happen. But in essence, I think there are some great things that are possible with these kind of tools. So it's good that you know how to use them, and we'll try to show you exactly how to do that for the course. So yes, I think that's the kind of general information that's important to go through on the course webpage. Again, you can find it back there if you are interested in looking at something further. It will all be posted here and available on the course webpage. Maybe I'll pause here and ask, are there any questions? And if you have questions, perhaps Kamyar can relay them to me just so I can make sure that I hear. All right, then let's jump back over to these lecture slides. We'll go through the rest of this kind of introductory part of today's lesson, and then we'll take a break. And one thing maybe just before we continue that I forgot to mention earlier is that the lessons are recorded. So let me actually just jump back here to the course webpage for just a second. We'll go through some motivation for the course in just a moment, but each week there is a lesson overview. And when you go to the lesson overview part of the page, there's a space here for lesson videos. We have only one thing here right now, which is from, it's something linked to another part of the lesson that is from a couple of years ago. But we'll post lesson videos here after class, usually within a day, because there's a little bit of editing and things like that. But we'll post the lesson videos so that they're available. Today's session, of course, is being recorded, and we'll record the sessions in the future as well and make them available on the course webpage. So if you're not able to make it to class, you are able to still see the lessons, although appreciate it very much if you do come to class, because of course it's nice for us to see people in the classroom. But yeah, I think we've kind of gone over the general ideas of what we're going to cover in the course. I'll give you a little bit of motivation now for why we might want to learn to program in Python. Like, what is the benefit? What's going to be appealing to you, for instance, for learning the skill of programming in Python? So yeah, basically, I mean, our goal for the first part of the course is to introduce the concepts of programming and how to program in Python. In doing this, we want to also make sure that we introduce you into ways to writing programs that are easy to understand. So things you easily can read through and understand what the program is doing, easy to share with other people so that when you do share your code, someone else who sees it can understand what you've done. But also keeping track of the changes when you write your program so that you know if you do something and you break your program that was working before, you have this log of the history that you can go back to and figure out what you changed and what might have caused the problem. We also want to make sure that introducing programming, we do so that you're writing programs that make your science reproducible. This is an important part of open science, is that what you do is reproducible and your results can be produced again by someone else. So we also want to make sure that we try to introduce these ideas for programming in that general construct. And we finally want to produce things like ways to visualize your data, to make it intuitive, to make it easier to understand, and something that's more accessible to people. And well, to kind of move in that direction, we can take a look at some examples here. So what you can see if you go to the course page is an example of some data. That's the kind of data we might typically want to explore a little bit. And this is a data file that contains global temperature data. If you look at this, most probably it's not going to be very obvious to you what it's showing. If you showed this as a way to look at your data set and say, wow, look at how cool this is, most people probably aren't going to think it's very cool at all, because it's a confusing format in which it is being presented like this as a text file. So not only is there just kind of a wall of these numbers and symbols and things in here, but even things like these kind of abbreviations up at the top aren't really telling you necessarily intuitively what your data set contains. So there's potential, but it's not that interesting. One way in which we could make this more interesting, the more accessible to people, would be to plot this as an XY plot of temperature versus time. So here on the example plot, we have time on the horizontal axis, and the vertical axis in this case is showing a temperature anomaly. So it's not quite temperature by itself, but it's a deviation from an average temperature, showing that, for instance, in the period before maybe 1935 or so, temperatures on average were colder than the average. And since the period from around maybe 1975 or so, temperatures have been globally on average warmer by up to maybe half a degree. So what this is showing us, of course, is now much more powerful in a way that you can look at this and right away you can see, instead of going through line by line, going, where's the temperature in here in this file, you can actually see quite clearly a nice visual representation of how temperature has varied over time and how temperature's been warming, for instance, significantly in the last 40 years or so, maybe almost 50 years now. So this is great, and this is much more intuitive, easier to understand. But there's one drawback in this representation, and that is that we have nothing spatial included here. These are global average temperatures, so we have time and we have temperature, but we don't have space. So another option would be to take those same temperature anomalies and plot them in map form. And this is an appealing thing to do because now we can see, for instance, here in January of 2020, how warm it was compared to average across much of the sort of Northern European and Asian continents. And for instance, how it was cooler in some places, but by and large, the picture looks like we were having a pretty warm January globally. We could see, for instance, here quite warm in southern part of Finland during that time by almost 5 degrees above the average temperature for that reference period in the same area. So now we have a spatial piece to this that makes the story, again, perhaps more interesting, that we can see temperature variation instead of in time, in space. But that's the drawback here as well, is that we've now lost our time piece. So maybe we want to see how temperature is changing in space and time. And that becomes a bit trickier to think about how you want to do that, because you've got multiple things you want to explore at the same time, multiple dimensions, and that's a bit of a challenge. But there are some clever ways in which people have been using Python to explore this idea of looking at how temperature changes in space and time. And I just wanted to show you a couple examples, because in the end of the course, we'll work toward things like this. I will tell you right now, we're not going to reproduce these examples exactly, but you can find the code for them online if you do want to see how to produce them. But the first one of these, I think the author of it, who happens to be a Finnish guy who's working for the Finnish Meteorological Institute, called this a pill packet plot, which I guess is because these kind of look like a package of pills in a that you might get from the pharmacy. And what you can see with this, if you press play in the animation, is how these temperatures have varied here for different years and for different countries. So I'm sure this is quite small. Maybe I can make it full screen for the sake of being able to see some of the countries a little bit better. But this is many different countries in the world. I don't know if it's all of them, but you can see now with this animation how temperature varied through time and in space. And of course, in blue colors, in this case, we're seeing temperatures that are cooler than average, and the red colors, we're seeing temperatures that are warmer than average. And so you see in this first half of the animation that, on average, okay, things were getting cooler some years, warmer other years, but you'll see an emerging trend as time goes on. And of course, as you can see here, what we're seeing is the emergence of the kind of red and orange colors, such that by 2017, which happened to be the end of this animation, you can see just by how much the temperatures have changed by comparison to the reference temperatures. So, some places in Mongolia and Russia, you're more than 2 degrees above the reference temperature. So the kind of average for that same place during the past. And pretty much everywhere you look on here, you're above 0 in terms of your temperature deviation. So that's a cool way to look at things. You see now this temperature variation in time and space. The same person, Antti Lipponen, also produced another way to look at this same data, including a forecast for the future. So this is another fun one to look at. Now what we have is sort of a radial type plot. So this line here would represent temperatures that are basically the average or equal to the average. So 0-degree difference from the average. And then as you go further away from the center, you're getting warmer. So like hotter than average. And if you go closer toward the center, you're getting cooler than average. But now things are clustered a little bit differently. So you can see Europe, all the countries are grouped together. Asia, the countries are grouped together, and so on. So instead of being in alphabetical order, where like, okay, you kind of lost a little bit of the geospatial piece, now we at least group things together by countries. And this is more or less showing the same data set. But again, it's another clever way to visualize the data because now you can see that these temperature deviations and how they vary will be kind of more closely clustered based on geography. And as we saw before, now we hit 2018, and you can see how much the temperatures have increased by comparison. And this is then using sort of some, I think there's some climate model here that's referenced, this RCP45 experiment that projects the temperature variation forward in time to the year 2100. And you can see what looks like a pretty scary looking forecast in terms of how much the temperatures will increase by comparison and where. So you can see, for instance, in Europe, we're one of the places where we would expect to see some of the largest increases in global temperatures. So anyway, that's the kind of picture that we're looking at. When it comes to learning what we're going to learn with the basics of Python, we can go from things like a data file that looks kind of boring and uninteresting like this, to being able to make visualizations that allow us to start exploring the data and gaining a more intuitive understanding of the data set that we have before us. And that's the direction that we're going to go. So yeah, as I mentioned, we have some slides to go through here that'll give us a little bit of background about computers and the basics of kind of computer, how they function, how they interact with programs and things like that. And after that, we'll take a break, and then we'll come back and we'll get into some more hands-on type stuff. We'll cover the rest of the course environment and then actually do a little bit of Python programming ourselves. So yeah, and I'll apologize that this is probably the most speaking heavy part of the entire course. This is first kind of introductory stuff. So I'm sorry if it gets a little bit monotonous here. We'll be much more interactive as the course goes on. But basically, for this part of the course, as I've already mentioned, we want to introduce Python programming. We want to develop your basics programming skills, and then also talk about some good programming practices. And in this lecture that we'll go through for the rest of the time here in the slides before our break, we'll talk about basic ideas of what computing is, talk about what a computer is and what programming languages are, and then look at the components of a computer program and how they work to solve problems. So as mentioned, one of the kind of key goals in the course is to develop these basic programming skills and help you to be able to understand how to write a program to do things that allow you to analyze data sets, for example. And the thing is that we know you're not computer scientists. We aren't either. And that's kind of a good thing. Computer scientists introduce programming in a different way than maybe we will here. And our idea with the whole course is to kind of focus on ways to motivate geo-oriented people to learn to program. And so we'll kind of go step by step and make some progress that way using motivating examples that are more relevant to us maybe than sometimes would be the case for a computer science type of course. And if you are asking yourself, like, do I really need to do this? This sounds like a lot of work. Well, in my view, yeah, I think you do. I mean, you don't necessarily need to be a sort of full-time programmer. You don't need that to become your career, that all you're doing is writing code. But basically learning these even basic programming skills will help you to do things that are quite useful. And it's kind of part of the toolkit these days. So when we look at things in how, you know, for me as a geoscientist, I'm interested in mountainous areas, how landscapes evolve over long time scales. And the way in which people are doing this is becoming more and more quantitative all the time. So there's a lot of use of sophisticated numerical models, a lot of ways in which people are linking laboratory and field measurements to computational predictions and basically using models to interpret their data. Because of this, programming is kind of becoming a sort of assumed skill, just in the same way that perhaps, basic cartography or knowing how to use a compass to measure things in the field for a geoscientist would have been a sort of a typical essential skill that you have. So learning these skills will help you to be able to do things like take part in the science that's going on now. And one of the things that's kind of fun is that you can basically, by learning a little bit of programming, extend what you can do with existing software. So you can do things that a program that you're using might not be able to do by itself. So for example, many of these GIS packages, ArcGIS, I'll maybe lump Google Earth in there, but QGIS, these kind of things, ParaView, which is a software for visualization, they are, in many cases, including a way in which you can bring your own Python code into that software and modify what the software is able to do. So, for example, here in QGIS, this is just an example of showing where the Python console can be pulled up in the software, and you can use the Python console to interact with things that you have in your GIS software that you've pulled up in some visualization. So when you have things like large data sets where you want to be able to do some things, kind of manipulating it by pointing and clicking and selecting like you would in a graphical user interface, it doesn't mean you have to completely separate that from what you could do with a program. You can actually blend these things together and extend what you can do with something like QGIS, which at least personally I think is super cool. Another reason that it might be interesting or appealing to learn to program is it is actually kind of fun. I think for a lot of people who come to university, you excel at certain things when you're in high school, like dealing with complex problems. And programming a lot of times basically involves breaking down something complicated into smaller pieces and writing a little code to deal with those smaller pieces to be able to do something more complicated. It also involves things like coming up with a strategy for how you're going to do that, testing your solution, which most of the time means just running your code to see if it works. But these are actually fun things to do because you basically are creating a little process and you say like, well, I'm kind of setting up my own little experiment here. And at the end, I'm going to run my experiment and see if it worked. And it can be, as noted here, a lot of fun. This is why programming is being introduced to younger and younger kids all the time, because you can find ways to basically make it like a game. And it can be a lot of fun to do that, of course, with the caveat here that when the code works, because it's also can be rather frustrating when your code's not working. But ultimately, what we hope in the course is that you'll have a mix of those kind of successes and failures, so that you feel like the successes can propel you through the times when your code's not working properly. So now just a couple words about the scientific method. This is something that I don't know whether it's kind of introduced formally in school or not, but at least it's a good kind of construct for how most science is working in one sense or another. And that is that we typically will define some kind of question and collect our background information about what that question is. And then on the basis of our background information, make some kind of hypothesis. And so, we may have a hypothesis about, I don't know, the way in which temperature would change or something like that. And then we can observe what happens in the future. We want to come up with some experiment where we can say, we think we have a hypothesis that we explain why temperatures have changed in different places in the past. And then we can test that with some kind of experiment. But we test our hypothesis using an experiment and collecting our data, hopefully in a reproducible manner, so that someone else could do the same experiment and be able to reproduce your results. Once you've done the test or run the experiment, you can look at the data and analyze it. You draw some interpretations and draw conclusions, and that may become the basis of a new hypothesis, and you go back and repeat the process. If you're lucky and you sort of have something that's quite interesting, you may then publish your results, and then someone, yourself or someone else, may retest what you've done. So that's the kind of overview of how science works in a general kind of process. With programming, we can basically benefit from things like gathering information and resources. So if we have scripts that can be used to pull information down from big web databases online, of course, that could be very useful. Performing experiment, of course, you could write a program itself that is basically doing your experiment and collecting the data from the experiment. The analysis is very often already going to be done with some kind of software, which you could basically either use some ready-made package, or you could come up with your own solution, depending on what kind of data set you're dealing with, whether there is even some way to deal with the data you have. And of course, the interpretation, visualization, these kind of things that come out of your data set would be very much useful to be able to use programs, because, of course, you can perhaps draw some nice visualizations that way. Now, in addition to programming, if we use good programming practices, so these are ways in which we make sure that our programs are more accessible to a broader audience, that we can reproduce our results. I mean, basically, that means that if we produce a figure, for example, that goes into a thesis, that you also include the code and how to produce that figure, so that someone else who looks at your thesis in the future could say, oh, okay, well, I see how they did that, and I run the code and I get the same result. This looks like it's not something that's been falsified or whatever. But also retesting. I mean, it makes it much easier for someone to confirm the results of an experiment if you provide the code and share the code in such a way that they can do that. So in terms of open science, these are the things that are really, I think, important for us to consider. And I think it's great if you're learning to program to learn this stuff now, so that in the future, if you're asked to contribute to some scientific data analysis or something where it's expected your results are shared with a broader audience, you're already like, okay, I'm ready to do that. I already know how to do all this stuff. Okay. Finally, a brief break from me speaking, and that is now time for another poll question. And this is about, what is a computer? And I'll ask you again to go to our poll site, and you can type in what your idea is of what makes up a computer. And again, like we did before, you'll be able to vote on the results that are contributed by the others. So if someone says something you agree with, you can vote and add your vote to their I don't know, running tally. And I'll just go here. And so we can follow what the results are as they roll in. Okay, so numbers are still changing a little bit, but I think a tool has emerged as a leader, programmable machine, and various other versions of similar kinds of things here. So yeah, I mean, a computer certainly is a tool for us. We can use a computer to do many different kinds of things. So I would say that certainly would qualify as part of the definition. And I think the second one here, a programmable machine, is probably quite close to what we would say would be a reasonable definition of a computer, because it is a little bit different, for instance, from a calculator. It can be used to do calculation, but calculators are not really, I mean, at least in the kind of traditional basic kind of handheld calculator, they're not really programmable. So, the ones where you can just kind of type in this plus that, or this minus that, divided by that, whatever, not a kind of graphing calculator, those are hard coded. They can only do certain things. Whereas a computer, what makes it different is that it has a program, and you can change the program that will then change what the computer does. So it's a little different than just being a calculator by itself. Although it can do the things a calculator can do, it's a little bit more sophisticated than that. Interpreting electricity as binary code. I don't quite know how to think of that one. I mean, yes, in essence, what happens inside a computer comes down to things being either zeros or ones at the very low level for how the computer is operating. And that's the binary part about it. So ultimately, everything gets translated to zeros and ones. I don't know whether I would say it interprets electricity as binary code, but it does in some ways operate using electricity and these kind of zeros and ones to store information, to make decisions. All of that stuff is kind of ultimately at a very low level. That's how the computer is working. The zeros and ones really almost includes logic in that, because a zero is often interpreted as false, a one is interpreted as true, and combinations of zeros and ones form the basis of things like logic that would be used in a computer. The hardware, software, and user interface is maybe a little bit more of that's going maybe a bit beyond what would be the necessary element for the kind of the core of what a computer is. So, I mean, it could be really just the hardware and the fact that it's programmable would define a computer. But yeah, for many of us, this sort of user interface is essential for us being able to use the computer as a tool. And so, yeah, I mean, I think we've got some great ideas here. And if we jump back to the slides for a second here, what we can see in the definition that a computer scientist would give is it's a machine that stores and manipulates information under the control of a changeable program. So that's why I kind of like this idea, this programmable machine idea, because that is basically quite similar to what this is doing. In the box diagram for a computer that you would see from computer scientists, basically we have input devices. So this could be a keyboard, mouse, whatever other kind of device you can use to give input to the computer to tell it how you're feeding in information. The central processing unit, or CPU, which is connected to the memory in the computer. Those are essential things. Secondary memory in this case would typically be things like a hard disk or some other kind of storage device. And then output devices could be speakers, could be a screen, could be several other things. A printer would be an output device as well. So what you can see basically is that there's information going in, there's some kind of stuff happening to the information, and there's information coming out. And that's basically what the computer is doing. So it's manipulating the information that you put in by way of what is in the computer's program, and hopefully making it into something that's more of a useful form than it was to begin with. And the key thing, again, that distinguishes it from something like a calculator is the fact that the program that is running on the computer is something that's changeable. It's not fixed. So it can be modified, it can be updated. In this way, I mean, if you have your smartphone, a smartphone is definitely something that would qualify as a computer. Your finger smudging things on the screen would be the input in this case. Output would be, of course, like what comes to the screen or the sound it produces or whatever. But you get regular updates to the software, at least if you've got a reasonably recent phone, and that's the changeable program part that's included there. So when we talk about computers, we can also talk about things that they are good at, or maybe not so good at. So there's things that computers excel at are well-defined, clear tasks. So if you tell a computer in a way it understands to add 2 plus 2 and return the answer, like here's how you would do that in Python, print 2 plus 2, and it gives you back 4. No problem. Computers are great at that. Also, usually good at data storage, manipulation, repetitive calculations. So asking it to do the same thing over and over again, whereas a person might get bored, a computer's totally happy to do the same thing hundreds of thousands of times. And then processing data or instructions. So these are things that computers are good at. We don't need to worry about the Python thing for right now. They're not so good at abstract or poorly defined tasks. So I would say, that calculate pi, if you told the computer to do that in Python, you're going to get error messages because it's not going to know what to do. You need to give it an equation or something. How does it calculate pi? An exception to this would be that there are now these things like these large language models linked to AI tools like ChatGPT. And if you ask ChatGPT to do something like calculate pi, well, it will give you something, but there's a lot of stuff going on in the background to process the language that you've typed something in, convert that to something the computer understands, do a calculation, and then give you a value back. So, it's not that computers can't calculate pi. I mean, here's the first thousands of digits of pi, and I think this is probably something that takes only milliseconds for a computer to calculate, if that. So that's not a problem, but you need to give the equation for what it's supposed to do in order to get this kind of value to be output. And there are some things that are simply too big to calculate. So Finland is host to the Lumi Supercomputer. It's roughly 200,000 cores. So that's pretty big, powerful machine. And even with this, there are questions that this massive supercomputer can't handle. So if you ask it where my car keys are, again, it doesn't have enough information to be able to figure that out. It's too abstract. So even this massive computing can't solve some kind of problems. And there are some things where, like, if you said, you want to run a climate model where you predict with 1 meter accuracy what the temperature is for the entire planet, it's probably also still too massive to actually do that kind of calculation within the memory constraints of what the computer can do. Even if it knew how to use a climate model to do some of those calculations, it may just require even more computing that's available than what this could provide. So they aren't great at everything. And in terms of a program, so just do a couple slides here about what a computer program is. These are some examples. So this is an old school Fortran punch card. So back in the day when you had to program using punch cards by basically making a big stack of them, typing in different things and punching out holes in the punch card to tell the computer how to run your program, or a slightly more accessible form, which is an example of Python source code. Well, what is it? It's a detailed list of step-by-step instructions that tells the computer exactly what to do. Because again, computers aren't big fans of ambiguity, of uncertainty, of kind of lack of clear instructions. So the program should be step by step, and it should be exact in what the computer is being asked to do. The program itself can be modified, of course, and sort of alter what the computer will do when the code is executed. And the word software is just another name for a program. So it's a step-by-step list of instructions. That's the kind of main thing. Programming language is basically the way we talk to the computer. So I've made a little modification to this slide from years past, saying that, I mean, in the past, I've said, unfortunately, computers don't yet understand our native languages. Well, that's true, but these kind of chatbots and these AI applications are getting better and better at interpreting things that we type in and converting that to something the computer then understands. There's a lot of computational stuff going on in the background, but we're getting closer and closer to computers like almost being able to talk. I mean, we're typing things in and the computer's interpreting it and giving us back typically somewhat meaningful information. So that's the language you use to talk to the computer. Programming language is like a sort of code. So it's instructions that we give to the computer that it can follow. A programming language is exact. So when you say to print something, there's no question what the computer is supposed to do. And it's unambiguous, meaning that everything in there is clear and precisely defined so the computer knows what to do. And so what this means is that every part of the program language has a precise form, that's what we call syntax, and a precise meaning, which we call semantics. So for instance, syntax for the print function in Python would be the word print, P-R-I-N-T, and then there's parentheses, and then whatever's in the parentheses would be the thing that you're asking to be printed to the screen. The meaning is to display something on the screen. So it should be intuitive, hopefully, what the print function does. And I think our last little thing here is just an example, somewhat silly example, about how to develop a computer program. So we know what a computer is. We know that a program is our sort of step-by-step list of instructions for the computer to follow. And now let's talk about how to make a program on a very general level. So I'll tell you right away that it's not always the best idea to jump right into typing in your code as your first step to trying to write a program. The thing you need to do is to follow somewhat of a strategy here that will help you. And believe it or not, following the strategy will make it faster for you to produce programs that work more reliably. And so the steps are laid out here. So analyze the problem. What is it you want to do? Determine the specifications. What do you need in terms of information to do what you want to do? Create a design. So in general, what are you going to do with that information? Implement the design, which is typically the part where you're writing your program. Test it, running the program. And then the step 6 here, if it's needed, would be to maintain the program. So if there's something like you're using a library where there's changes to the library, you may need to update your program to work with the new version of some library. And I always go to this silly example of dealing with temperatures. So as an American, the US is still using Fahrenheit system for temperature. So it's 70 degrees Fahrenheit would be a lovely temperature, 90 degrees would be hot, and water freezes at 32 degrees Fahrenheit. And as you can see, it's a very intuitive system. And of course, the reality is that, well, living in Europe, temperatures in Fahrenheit don't get me very far. So if I want to know what clothing I should put on, and I know what I should wear if it's Fahrenheit temperature, I know exactly what to dress in. What I need to do here is I need to be able to convert temperatures from Fahrenheit into Celsius, or vice versa, from Celsius into Fahrenheit, so I know what clothing to put on. And I think a program could help with this. So our first step is to analyze the problem, and that is to basically figure out what do we need to do. In this case, I think the problem is fairly clear. I want to be able to take temperature in Celsius that I might get from some FMI app or whatever, from some web page, and convert that temperature from Celsius into Fahrenheit so that I know what clothing I should put on. Now, for the specifications, well, I need to describe exactly what the program will do. In this case, I'm not going to worry about how it's coded. I'm just going to say, okay, well, what it should do is it should take a temperature in Celsius and convert it to a temperature in Fahrenheit. That way, I am dealing with temperature scale that I'm familiar with. The next step, once I understand what the program should do, is to create a design. This is often called something like pseudocode, which you can write down essentially in just normal language what your program should do. What's the overall structure of the program? So for me, for instance, I would say, okay, well, first, my program should take in a temperature in Celsius. It should then calculate what that temperature is in Fahrenheit, and then print that temperature in Fahrenheit back to the screen so I know what the temperature in Fahrenheit would be. If I wrote down those 3 lines, I already have a script basically for what my program should do, and I can understand that quite easily. And then I can move to the next step, which is to implement the design. So this is the stage where I take my script that I've just produced in terms of my list of things I want to do, and now I convert that into Python. I take my sort of first step of inputting in the temperature and convert that into some thing in Python where maybe I use the input function to ask the user for a temperature in Celsius. Then I have my conversion. Maybe I put in the equation into a Python program, store that as a value, and then print it back to the screen. This is basically just translating my pseudocode into a programming language. Could be Python. We're kind of agnostic as far as language goes with the pseudocode part here. So maybe if you're more comfortable in R, you could just take it and do it in R, or you could do it in C or C# or whatever programming language you want. But yeah, that's the kind of coding stage. Then after that, I want to run my program. Well, I mean, I can think of things and say, I should run it, see if it works. Well, how do I know if it works? Well, I do know some things. I know temperature of water would freeze at 0 degrees Celsius, and it also freezes at 32 degrees Fahrenheit. If I run my program with 0 degrees Celsius, I should hope that it gives me temperature back of 32 Fahrenheit as being the equivalent. So in order to know that the program is working, it's great that it runs and doesn't produce errors, but actually testing to see whether the results that it produces are reasonable is an important part of this as well. Otherwise, it runs, but do you actually know whether it works? And finally, In our simple example, most probably I don't need to do anything to maintain the program. It's going to be quite simple. But of course, there are things, maybe someone else wants to be able to do something different, like, well, they want to convert temperature from Fahrenheit back to Celsius. Okay, well, if that's something, someone requests, then maybe I would write a program or add something to my program to do that conversion as well. So this is just kind of an optional step to program development. Okay, I think at this point I have spoken for quite a while, and it's certainly time for a break. So why don't we let's take 15 minutes. I'm going to skip this little recap thing. And when we come back, you can open your web browser and go to the GeoPython course page. But we'll continue at 10:40 with our next part of our lesson.